Finite element method. We've been building towards finite element. Yeah, that's on, that's sharing. So we've been building towards this thing for a while now. I thought about trying to make an assignment on this, but honestly, it's a bit too complex. There are entire courses dedicated to the finite element method. So it's going to be under the general comprehension, because most of you guys are COMSOL familiar anyway. You may as well understand what on earth those options are actually saying. But I don't have an assignment question on it, and any questions would be strictly comprehension anyway. But considering the popularity of it, it's kind of good to, I can't let you guys leave numerical methods without at least having some kind of understanding of what finite element method is doing underneath. All right. FEM, super popular for a wide range of applications. It's an integral technique, similar to finite volume, in that it doesn't focus so much on the continuity of the derivatives as it does on the integral properties of the equation. So, thank you for the loan. The finite difference, you have a bunch of those guys, right? And what you have to say is some kind of approximation. Okay, so you're doing central difference, and then this derivatives between that data, between those data at those points, satisfies some kind of equation. The alternate is something like finite volume. Finite volume says, no. Just worry about the integral of all the fluxes around the boundary, and that's kind of the quantity of interest. And the nice thing about that is it has different stability properties. It's not so concerned about things like, if you remember when we had realistic data that went like this, the gradient was amplified, right? Integral tends to smooth out any kind of errors, any kind of approximations, whereas any kind of derivative-based method tends to exaggerate it. So what we're actually going to find is that finite element method, even for equations like my favorite heat transport, right? This is second derivative in T. You have a term that goes like that, right? FEM does not, in general, actually satisfy that. The slope is not actually usually continuous. It's not even defined. Right? So a typical example of FEM would have something like that. Or if we're doing some kind of quadratic element, we would have something like that. And the second derivative here isn't even continuous. Right? Not only is it, or sorry, it's not even defined. Not only is it continuous, but like the limit does not exist for the second derivative. Right? If you look at it, it's something like that with a cusp. And yet, FEM solutions are actually more mathematically rigorous and robust. And that's because of something called the minimum MWE. We'll come to it. We'll come to it today. Minimum weighting residual, MWR, not MWE. All right. FEM is super good for complex geometries. Why? Because we can represent it with triangles, right? And a triangle, if you have something small, you can get as small as you want. You just keep refining your triangle. Right? On and on and on. So any kind of complex geometries or anything like that, no problem. FEM's got that. Irregular meshing, no problem. Material properties, also no problem. You can tweak the method. FEM, there are, I don't even know how many variations of this thing there are. What was that website? Periodic table of finite elements. Was it that one? Yeah. So I could send this out to you guys. No, it's just a publication in SIAM. Okay. There's a website. I'll just send it out to you guys. There are families of finite elements. Talk about what elements are. I think there's actually a link in here. That are able to like kind of adapt to different types of physics and things that you would want and represent. But it all falls under this big family. You can do dynamic mesh refinement, which means if you wanted to, because you can work with the regular meshes, if you had something that was in 2D, you had a giant triangle and you realized that something important was happening over there, you subdivide it super easily. Subdivide, subdivide, subdivide. right? And you can do that in large part. There are three different ways to refine things. The easiest way, which is called H refinement, is just is literally just halving the step size. And you can, okay, that one's not really admissible because that's a hanging node. Neither is that one. You get the idea. You just make it smaller and smaller and smaller, and you can do that iteratively through some kind of like parent algorithm. COMSOL does that, by the way. There is an option for that. They call it remeshing, right? So you calculate through a solution, you identify where your largest gradient is, you go back and you refine the mesh accordingly, and then you just rerun your calculation. And if you're smart, right? Show you guys this. Say you start off with an interval, blah, 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 right? And you've got some solution that does this, right? You've got nothing, 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 something, something. You calculate it once, it looks ugly. You end up representing it as a line. You say, okay, there's your gradient, right? So it goes back and it does another pass. And now it does a much shorter mesh here. These guys haven't changed. So generally speaking, you could actually keep with some confidence your answer out here, which is super useful when you have a giant, a car engine, and all you're worried about is the thermal shock from your brakes, right? You localize that mesh refinement, and you don't necessarily even have to recalculate some of that stuff. Generally speaking, you do for consistency reasons, but you tune down the resolution on that guy, right? You get it smaller, and then you refine accordingly. Boundary conditions, they're super flexible. You can actually solve boundary physics. What that means is, because finite element is n dimension, is dimensionally agnostic, what you can do is solve two-dimensional problems embedded in 3 space. So if you had something like, you guys have done electromagnetics, right? You know what the skin effect is? Right? So skin effect, you have an AC current, it localizes all the charge on the outer surface of your material. Why bother mapping everything on the inside? Right? If you're doing, what is it, the Faraday cage, the dude's like sitting in a chair inside the bird cage, right? Like, if you have that big thing, and you know that all the charge is only going to be here with like, a couple microns or something like that, right? Why bother meshing anything in the inside if we don't need it? You just don't bother meshing it. You just do that on the outside. Super useful for, what was it? What did the guy talk about last year? I think it was some forms of aerodynamic calculations where all they were really interested in was the fluid flow around the surface of the airfoil or the object. It was something more complicated than an airfoil. I think it was car body optimization, something like that, right? Like, because a car body has so many like ins and outs and rounds and everything, right? What he ended up modeling was ANSYS is also FEM. Everything that ANSYS does follows under FEM, with a few exceptions. I think technically LS-DYNA is also part of that, and that's explicit finite difference or something like that. Yeah. But yes, right? So this is something that ANSYS would do, right? If you have, so say you have some like kind of curve on your car, right? And you're looking at the fluid flow, and you're going to see it's going to do one of these guys, right? If you have some super complicated geometry and all you're looking for is this, why bother modeling a lot of the air out here, which isn't actually participating? A lot of your dynamics is happening right on the surface there. So can you just, instead of doing a 3D problem, map it out to a 2D problem? You have massive, massive computational gain doing that. The difference between ANSYS and COMSOL, ANSYS is more purpose-built. So they were kind of like the first ones to the market. And they said, okay, well, you're doing car body optimization. Here is a computer code that's specifically geared to car body optimization. It uses the boundary element method, blah, 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 blah. You are doing some kind of brittle fracture in buildings, right? Here is a dedicated one. And then they they started with pillars and then tied them all up together. COMSOL started with the base and branched out like that. That's kind of the difference between those. COMSOL is better for multiphysics because it starts from the common base. But honestly, like ANSYS is just much more comprehensive because they've been doing the same problem for 30 years, right? So they have blah, blah, blah elements. Have you guys done like ANSYS, CFD? There are, especially when you're in structural mechanics, they start talking about the different types of elements that go into it. You might have like come across it and like the grad student said something and you're like, okay, right? That is the type of boundary element that is particularly geared to this type of methodology. I'll show you guys what it means. All right, motivating example. We have our good old population growth. At T0, it starts off at 1. Everybody should know, especially 3D04 people, what the solution to this is. It's just exponential decay. Okay? So far, so good? No confused faces? Good. We want to approximate this between 0 and 1. And we're going to use a straight line. Super easy. Is a line going to exactly reproduce an exponential? Is this a line? No, right? So it's not going to, but we're going to try anyway. Okay, and what we're going to do is we know f at 0, call that time, is 1, right? And we know our analytical solution should be, right? So we know that our analytical solution should be something like that. Okay, we're going to start off with 1, and we're going to go, this is A, I don't know why I said A is equal to 1. It's 1. Okay, one option is to just throw the equation of a line into that differential equation, right? So we're just going to say, we're going to postulate some solution. We're going to say that y of t, I know I switched between f and y there. Call it f, right? F of, there you go, not even y of t, f of x, just to be confusing, okay? What this is 1 minus x plus xb. So it's a straight line, it's starting off here, and it's going to get over here to some value b. Where's t1? So far, so good? Straight line, basic straight line. All we're going to do is that, the magic, the only tunable parameter, the only degree of freedom we have in this is the parameter b. How would we find b? One way, we just throw it into our differential equation. Since we know the first derivative is negative times the value, we just throw it in, the derivative of this guy with respect to x. You get negative 1 here, you get 1 there, b minus 1. Okay, that's this side. And f at 1, this guy goes to 0, this guy goes to b. Right? Rearrange and solve. Simple, super simple algebra. That means that our approximate solution, you plug this guy back in here, is f of 1 minus x over 2. Who thinks this is going to be a good solution? Obviously, right? Because otherwise it would be a pretty piss poor example. When you actually plot it, it looks like that. And this, okay, you've got your boundary condition on one side, right? You've got your answer on the other side, but this is like that. That's a fairly large difference. Anybody know why this is so bad? What did we actually plug in? What are we actually matching? Too early in the morning. Well, we're still working with a line. So there is, okay. What would a better solution look like? This is the one, this is our actual answer. And when we do this direct method, we get that. Like that, who thinks that this is a good line? right? What would a better line look like? Got to be a straight line still, no curves, right? But like the one that we would actually want is probably going to look something like that. It's still going to be locked to that because that's our boundary condition. We know that for sure. But like there is a better line. The magic is when we substituted in this, we were only focused on the x is equal to 1 position, right? We were only looking at this point. So over here, the slope here is roughly, because it's not actually the correct value, right? But it's roughly that value. And that fixing the slope, you've got like that, which doesn't actually match it very well. Gotta be careful with going ahead too much. Any ideas how we could get a better solution? Ignoring my previous scroll. What does, this is our current one. This is our better one. What's that? How do you mean? How do you mean? Oh, like that? Yeah, but you don't know what your endpoint is. That's the problem. So that is the direct method. That is the one that we do. This point here is consistent with the differential equation, right? But it's only consistent after a straight line between here. But if you don't know that beforehand, you have to plug that in and rearrange it, and then you get all the other stuff. So what is this one? Why are we saying that? Is there any disagreement that line 2 is better than line 1? Okay, why? It's closer. Define closer. Right? How would you define that mathematically, though? Right? Do you ever want the residual by itself? So if you're talking about minimizing the residual, right? So the residual of this guy, right answer, is R is equal to, oh, sorry, what's my original equation? Y is equal to negative Y. I think that was the original one, right? Yeah. Okay. So the residual is going to be something like negative Y minus Y primed, right? Could I rearrange this guy? Could I actually say this was Y primed plus Y? Just move it over to the other side? Yes, right? So what do you always have to do with the residual? You got to square it. You always got to square this stuff. Squaring will normalize because you don't, if you just want to minimize anything, if you want to minimize the residual, your solution would end up being a straight line going all the way down because that would be a negative. Negatives are less than positives, so minimize. But what you actually mean is you're going to minimize the squared error, right? So that you're avoiding all that. Okay. Excellent answer. Let's try that. Least squared minimization of the residual. Good news is we've got least squared regression, right? This is where all this stuff is tying in. Don't think about that too hard. That's not actually the right path whatsoever. It's tempting, but it's not the right answer. All right. So let's rearrange this stuff. I'm not going to write this out just because it's literally written right here. Okay. We move everything over to one side. We plug in all our values, still assuming a line. We've still got a line. We just chuck all that stuff in. We get this equation for R. Square it. Simplify. If anybody's still actually doing this by hand, like by all means, but honestly, like Mathematica, Wolfram Alpha, stuff like that. Okay, we've got R squared, and now we're going to integrate it. So technically, R squared depends on all values of x between 0 and 1, which is boring. What's a lot easier is to integrate it, and you minimize the integral. And especially with a line, because then you're summing up everything that's above 0, below 0, etc., etc. Integrate this bad boy, and you get that guy. Okay? So f is your total error. What do we do next? Like first year calculus. You've answered every other question. Anybody? Somebody over here? Just take the derivative. That's it. That's all you got to do. It's funny sometimes, like you get so far into math that you lose sight of like the thing that you learned in like second year or second week of like first year calculus. Yeah, this is a polynomial. You can always find the minimum. It's equal to super simple, something super simple. You set it equal to 0. You find b, and you plot it, and kaboom. Hallelujah. Much better fit compared to this guy. The reason why is because you're focusing on the integral difference. That's the magic. The integral difference between your postulated solution and your real solution. That's what you're actually trying to minimize there. If you go back and you look through the math, what you see is that what we did, we calculated r, we integrated it, and then we took the derivative with respect to b. Right? That was the path that we went. You can always remove that derivative inside your integral. So this guy, right, we've minimized the residual here. We had something like that. Let's just bring this guy inside the integral. Why not? We get this equation, and we're just going to generalize 2 dr by db into this weirdo function v that has yet to be determined. Okay? So this worked. The problem with this one is that we had a lot of symbolic manipulation in here, right? We rearranged all this stuff. We did an integral, and we didn't just do any old integral. We did like a symbolic integral, and then we took a symbolic derivative of a symbolic integral, and we found like our actual solution. So even Gemini would get confused about like how to actually put this into a computer system without something like Wolfram or something behind it, the computer algebra systems. Okay, so we want to use those ideas. We don't want to do this method exactly. This idea that 0 is the integral, 0 to 1 of r times some function v, right? If the function v is 2 dr by db, then we recover our previous method exactly. What else could we do? This is called the method of weighted residuals. That's our residual. That turns into our weighting function. And let's play with it a little bit. We can integrate that form, NWR, to find the parameters with some convenient choice of v. If we do dr by dv, then we have to worry about our symbolic differentiation. We don't necessarily want to do that. One option, which I'll talk about later, is just to say that v is equal to x. That's all. Instead of, it's a weird way to do it. It turns out to actually be mathematically robust, especially when you get into Galerkin. Let's say v is equal to x. You multiply this through, simplify. You still have to do some symbolic logic, but now this integral and this differentiation is much easier to do, right? Because we didn't have blah, blah, blah integrated over something was kind of complicated. And it is very close. 2 over 5 is very close to 5 over 14. So we've done a much simpler calculation already. We've done a simpler calculation, and we've got a decent answer. Okay, so we're moving towards the right way to do it, quote unquote. But we're still doing analytical integration and differentiation in order to calculate that integral. Do we want to do analytic symbolic integration manipulation? No. What do we want to do instead? Told you guys this. I hinted this like 3 or 4 times at this point. How do we do an integral? What is the cheapest, easiest, fast and dirty? It was the basis for assignment 4, question 3. It is the correct answer. Gaussian quadrature. Gaussian quadrature, I told you this was coming back, right? Gaussian quadrature says when you have an integral, right, between -1 and 1, that's just a coordinate. You can always do a coordinate transformation. There was a reason why I was like rambling on and on for like 20 minutes about, triangles, barycentric, right? All that crap is packaged into something like COMSOL. That's what COMSOL is doing, right? Can you imagine like having to build up like an FEM method to do that? Terrible, okay? What this is saying is this guy is approximately equal to f at, what was it, negative square root of 3. I think that's, or is it 1 over 3? Is it 3 or 1 over 3? I think so too. Right? Plus f at square root of 1 over 3. To like 4th order accurate. And this is the analytic answer, analytically, to this integral. Let's just evaluate it at 2 points, which we can do because we know that our solution is a straight line. We just say, what is the value at this x, and those two sum together is our integral. To 4th order. Yeah? With a convenience choice of v, recalling that we would have to like do the coordinate transformation and then evaluate that line at those 2 magic points. This is the answers that we get. You plug it in and we recover b is equal to 2 over 5, which is what we calculated before, right? This turns into, because we have to scale between 0 and 1 and -1 and 1, these become our magic Gauss points. You plug that in and all you have to say is your residual times x at x is the first Gauss point, plus that at the second Gauss point. You sum those 2 guys together and you solve for b and you're done. There is no more symbolic logic. You don't have to do the integral. You don't have to do the derivative. It's just that. It gets wacky because you have to do the coordinate transformation, right? This is between 0 and 1, and you have to transform back to -1 to 1. That's fine, right? But at some point in FEM method, you're going to have, your integral is going to be between, I don't know, -73.87 and positive 63.72, and you're going to have to rescale it, and it's going to be math through the wazoo. It's going to be a giant pain in the butt, but you can understand how it can be algorithmically done, and then you just chuck it into a computer, set it going, and off you go, right? That's the magic of FEM. You bring everything back to this plain old integral. You know what your Gauss points are, and you just evaluate your things, and you're done, which is fantastic. And you get, actually, very accurate answer. It's not the best answer because you have lost those analytics, right? Gaussian quadrature is only order 4 accurate because it is based off a cubic, but it's super easy to evaluate. So, recap of what we've done. We have said our function, whatever it is represented by a line, right? Spoiler alert, what we're going to do is like reconstruct our entire function over the entire domain as a sum of lines. That's a linear basis times some weighting factor, which is our b in this case. I already erased it, right? B determined the height, the character of that line. We're just going to tag all these guys on, sum them up. That's going to be our linear basis. We found a shockingly simple integral expression that minimizes the error between these things. So instead of having to do it quote unquote properly, where we take the residual, we square it, we integrate it, we take the derivative, we set b is equal to 0, right? This is just for straight lines. Imagine if we were using quadratics. All that would be even more complicated. 2D, 3D, giant pain in the butt. No problem. You just chuck it into this and off you go. We perform the integration exactly up to cubic order using Gaussian quadrature. And then we solved the linear system, right? This turns into something where you have some kind of, okay, it's bad choice of parameters here. You have an unknown value here times something is equal to something else. That's a linear system, right? What we're eventually going to do is we're going to have a whole vector of these unknown parameters. We're going to have to solve for them simultaneously. We're back to linear systems. So far, so good. All right. Nobody's fallen off their seats yet. Let's get through. I'm going to try and get down to meshing the domain. Okay. The formalization of the finite element method. We're still working on the book. I'm still not sure why it's not formatting correctly, but this should look better than this. Okay. What you have in general with some kind of differential equation is some operator. So U in this case is your solution. I apologize. The nomenclature is all over the place. You have some operator, which are differentials, right? You've got the Laplacian, K, grad, T is your unknown, and you have like some kind of constant information over on the other side. You have that defined over, why is there an S there? Oh, that's a dollar sign. Over your domain. Omega is COMSOL's domain, that's where I got it from. Okay. Let's just keep it to 1D because that's easier to visualize. Maybe we have boundary conditions on the outer surface. Delta omega is what, again, COMSOL's notation. We do not know U, and we will never find U. We will never find the exact solution because the exact solution is analytic, and we're not going to do that. We're going to find our best guess. Oh, geez, this came out really bad. Okay, what we're going to do is we're going to find our residual, a differential operator on some unknown function minus our source term, and we're going to try and minimize it. The exact solution, if we had the exact solution, what would this guy be? For the exact solution would be 0, right? Moreover, not just would the integral of r squared be 0, but actually every single r squared everywhere would be 0. Actually, not even, yeah, okay, r squared or equivalently r would be 0 everywhere. We are never going to find the analytical solution. So instead, we approximate it. One thing that we learned, I wasn't joking when I said like FEM really does like draw in different chapters from all over the book, right? So what we're going to do is we're going to approximate it as an interpolation function, right? Back to that. Fortunately, it's pretty easy to conceptualize. FEM notation, usually you would say that U sub H is your approximate solution. I'm not sure why. I think it's like one of these mathematical formulation things, rigorous notations. So what we're going to do is we're going to say that our approximate solution is a linear basis, is expressed in a linear basis. What the heck does that mean? It means that it is the sum of some weights times some shape function. So phi sub I is going to be our straight line, for example. And as omega changes, the slope of our line is going to change, right? Omega is the parameter. Is that omega or W? That's a W. W for weights, okay? So as our weight changes, right, we still have the same prototypic line, but now the magnitude and the way that that line is going to behave is going to be different. It doesn't have to be a line. It could be a Gaussian curve. This is radial basis functions. That's exactly how we did radial basis functions. We said f was equal to the sum of some weights times our kernel, which we could say was 1 over r squared. That's Euclidean, right? It's all related. It's a linear basis. That's magic of it. Nice thing about a linear basis is that we can express it as a linear system and solve it using linear system solvers. That's that pathway. Yeah. Nice thing about this guy is that your weights are a set of constants, right? Obviously, what's going to happen is that your weights are actually your degrees of freedom. That's actually where your solution lives. And then it's expressed, your total solution is some combination of your weights and your prototype functions, your shape functions. Gradient of the approximate is super easy because they're just scalars. They just goes inside the sum. Looking at minimizing the residual with the MWR method. We want to minimize the residual everywhere. We're not going to do that. Instead, what we're going to settle for is minimizing the integrated residual squared everywhere, as far as we can get. Which kind of amounts to curve fitting, to be entirely honest. We're going to use this MWR, which is like a generalization which includes the way that we originally did it. It's called a weaker statement. So at this point, if anybody's come up against something called the weak form of the differential equation, you might have come up with it in COMSOL. It talks about it quite a bit. We're going to get to it not tomorrow, Thursday. The nice thing about the MWR is that it is a weaker statement for the optimization than the one that we originally did. Then the integral of the square times the derivative. This turns into an easier thing, and we'll see why. If we said that V was 2 dir by dw squared, we would plug that in and we would recover the original way we did it. Right? You just undo that transformation, you get this guy. That's exactly the way that we did it. No problem. If we said that this function, this magic function V, was like delta functions, and delta functions that only were non-zero, right? If we said that it was this, we actually exactly recover our co-location methods for solving boundary value problems. You remember where that one is, what is it? You interpolate, you say that your solution is the interpolation of a bunch of points. That's that one. It turns into exactly that. But instead, we're going to do something else, which is called the Galerkin method. So again, you go through FEM, you're going to get into that. And what this guy says is that you're going to use as your test functions, these V and the minimum weighted residual, you're going to use the exact same functions, the exact same prototype functions, shape functions, as you were going to use for your solution anyway. If we're doing lines, that turns into an X. Remember how I said that we were going to worry about R times X, and I didn't say why, we were just kind of multiplying by X? That's why. Because we were approximating everything by straight lines, straight line is just proportional to an X, we just chuck that in directly. And we're going to say this is 0. This is the last part, and then I'll let you guys go. When you have, here's my pitch for like linear algebra, okay? Does this statement remind you guys of anything? At one point, so this course, we're going to swap it and we're going to put it into a second year course. Honestly, like I'm really thinking we should like start off with linear algebra for like 2 or 3 weeks and then go into this stuff. because that would be like, instead of like kind of building on it and then me coming down, this is like what, the second last week or the third last week or something. And here's like this key concept in linear algebra. And like, honestly, we could start with that and build up, but it would just be mind blowing, especially for, I think probably for second years. I'm not sure. I'm not sure I understand enough about linear algebra to give that a good pitch. Okay. Does this remind you guys of anything? You integrate two functions, and that integral is 0. Orthogonality, right? Click, 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 right? It's all linear algebra. That's the magic to it. And orthogonality means, right, that you can't improve your answer, that one function doesn't depend on the other function. They are independent in their integral. So what this is saying is that, I have to be careful what I say here. When you have satisfied the orthogonality condition, it cannot be any better. That weight, that coordinate is as good as you're going to get, right? Same way with coordinates, right? If your coordinates are orthogonal, y and x, right? And you're looking for some point. If your coordinates are orthogonal, once you're over here, you can't change this anymore by moving it. If you're not orthogonal, then maybe you move it over here a little bit, maybe you move it over there. You have to like do the whole thing all together. The whole nice thing about orthogonality is that you don't have to worry about that. Which means once you have the weights for which this guy is 0, that is analytically as good as you're going to get. You will never get better. It does not mean that you actually have to satisfy your equation. Right? This is the big trick. If you look back to this guy is dx squared, right? But if you're just representing it by straight lines, the first derivative doesn't even exist, let alone the second derivative. At this point between these two, you don't need to. This is the weak statement. It doesn't have to satisfy this equation exactly. It just can't get any better. It's 9:20. See you guys on Thursday. We'll pick it up from there. So, finite element method, right? What we did last time was define and kind of explore this idea of the method of weighted residuals. So the whole idea is that you want to solve your equation, but instead of solving your actual equation, you're going to write out your residual, right? You put everything on one side, you define that as your residual, you say that's equal to 0. In the analytic case, you're never going to get the analytic case, right? So normally what you would say is you would square that and you would want to minimize that. That turns into be inefficient because then you would have to do like symbolic logic to integrate. That's boring, and differentiate, also boring, right? So we're going to use our Gauss points to do our integration for us, keep it numerical. And instead of this r squared, we wrote this out as RV. RV is called your test function. We're about to explore that in terms of a different formulation too. And it could have different forms, right? So the most trivial one is 2 dir by dw. W is your weights, right? And if you plug that in there, then what you're doing is you're minimizing r squared again. Okay, that one's kind of obvious. Collocation scheme. So this is actually solving your differential equation through interpolation, right? Now you've got your collocation points, and you just say v as your delta function. So it's only non-zero at particular points. When you minimize that, you have found your interpolated function that gives you your best answer. The Galerkin method, which is one of the underpinnings of finite element method, the most common one by far, says that what you want to do is whatever function, whatever basis you're expressing your solution in, you're going to use that as your test function too. And there are reasons why you would do this, and we'll come to that with assembly. Okay, so what that means, oops, I had there. Took it out. Where? Oh no, still here. Good. Okay, so what we're going to do is we're going to express our solution the same way we've been doing for interpolation and everything else, right? What we're going to say is that I can barely even see some of these lines here. There we go. Right? We're going to say that our solution is some sum of weights times a shape function, right? So generally speaking, our shape function is going to be something like a line, for example, right? And a line that's only defined between a certain range. If you want to do some kind of shape like that, what you've got is one line here, another line there, right? And the curvature of those lines, the angle of those lines are defined by your weights, your W's. Okay, and what we're going to do is we're going to use this line shape function with different types of elements. We're going to chuck that in, and we're going to use that as the in our minimum weighted residual too. Okay, and what that's going to mean is that when we find the solution, we're never going to find the right solution. All we're going to find is the best solution that we can within that space. What space? The space of our shape functions. This is much more general. We're going to see why. When we define our shape functions, what we're going to be doing is defining them on these elements. So we're going to have to chop up our large domain, whatever we're actually trying to do, into these small ones, right? And I think we spoke about this before. The smaller the element, right? There are a finite number of elements in this picture, right? Finite element method. That's one of your finites. There are two finites in finite element method. One of your finites is just how many partitions you had. If you had infinitely small and you had infinite many of them, you would find your exact solution. We're never going to have that. Therefore, we have to approximate it. And what MWR is saying is that that is the best one we can find. Okay. How are we going to do that? Triangles, or more generally simplices, are the easiest way to do that, right? So in 2D, that's going to be an interval, super trivial. In 1D, that's an interval. In 2D, that's a triangle. And whatever shape you want, right, you can always map triangles in to fill that out, right? This is what COMSOL does by default. So even when you're going around the curve, right, you're going to get to some kind of resolution limit because triangles have straight sides. COMSOL actually has some curved boundary finite element something. It's in the documentation. I can never wrap my head around it. But I should mention it because COMSOL at least talks about it in their documentation. Alternately, if you didn't want triangles, you could make quads, right? Easiest way to do that is just delete any of these lines, and what you're left with is a quad. Quads are, generally speaking, more stable, actually, because you have a bit more flexibility in the way that they're implemented. But you have problems with mapping, right? Because when you get down to a point or something like that, it's hard to map out and keep those sides separate. And if they get too small, then they're degenerate. Now you're back to a triangle again. So you may as well keep with a triangle. Yeah. Sometimes you'll want to mix them. So with CFD, what's kind of common is if you have a curve like that, you have boundary elements. And they are quads that are really kind of glued to your boundary. You may have seen these when you were building your models. Right? And then you do triangles after that. So then you get quads that are nice and will map out those streamlines along that curved surface, but then you get triangles to like scale it up and make it a bit more robust. There are entire computational packages, very expensive ones, specifically dedicated to meshing. What is it? Qubit, is a big one that's pretty common in CFD and in the nuclear sphere. Gmesh is the open source version of it. I'm not going to say equivalent. There are a few other ones that are around that have different types of mesh. Apparently in CFD, a common one is actually hexagonal prisms. And they have computational advantages if you do a hex that's kind of extruded that way. And it just kind of goes on and on and on, but it's a bit deeper than like this is a full course on FEM at this point. Okay. Notice every single one of these triangles is just a scaled and like rotated version of the primitive triangle, right? So if you remember when we were talking about Gauss quadrature, right? Everything was kind of mapped back to that prototype triangle, that prototype shape. We can do the exact same thing. Let's talk about types of elements. Any questions on that one? Cool. Okay. Elements are the type of function that you're going to fit over each one of those. Sorry. The type of element relates to the type of function that you're putting on that shape. So for example, if your element was a line because you're in 1D, you could have a line, you could have a point that's flat across, you could have some kind of quadratic, that's not a quadratic. You could have some kind of quadratic. You could define these things in different ways, right? We're going to talk about different ways to do that. All of them are going to be parameterized by these W coefficients. Those are called your degrees of freedom because they're literally how much you can kind of move this thing around. The different types of elements, what you guys used in ComSol was something called Lagrange elements. Typically Lagrange elements of order 2. If you go into, which means you're doing quadratics and you're defining I'll show you guys. Typically different ones, there are different reasons why you would do different types of elements here. Okay, your parameters could mean different things. The most obvious one is to say that your parameter is the value at these nodes between your elements. Yeah, I just don't want to get ahead of myself. Yeah, no, that's okay. 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 Another option would be the first derivative, right? This could actually be the derivative between here, between here, between here. You could have one as the second derivative. You could have one as points on the node and another one in the middle here. Maybe you have points on the node and your second derivative here. Why would you do that? Because this is your divergence term, right? So by catering the different types of parameters and the different parameterizations, you can kind of fit the element to the type of physics that you're looking to do. One of the magic points, though, is depending on where your DOFs are, you're going to have different continuity conditions. Because this point is shared between this guy and this guy, right? So if you're fixing your function value here and it's shared, then you have a continuous function. If you're fitting the gradient here and this point is shared, now you have something that, sorry, try and draw this a bit bigger. So if I had the slope value, the gradient, instead of the function value itself, I could have conceivably a situation like this, right? You don't have a continuous function, but your slope is the same on either side. Is this better, right? For elasticity, actually, yes, because your strain is equal to grad u. So if this is your u function, right, it doesn't actually matter. If you had something that looked like that, a continuous function, that's great, but the gradient here isn't defined. It isn't defined analytically. Within MWR, it is defined, but analytically, you have two straight lines and a point, and this derivative doesn't exist. So instead, what you can do is define the gradient, and now your gradient is continuous even though you have a jump there. Right? This is like one of the ways that you can kind of like twist this thing. There are other reasons why you wouldn't do this, by the way. But that goes on and on and on. This is why like textbooks are dedicated specifically to FEM. There are graduate level courses. I don't know if Mac offers them, but other universities do, right? That are specifically designed to FEM because it just goes on and on and on. It's also why, like, if you look at ANSYS or I think Abacus is another one, COMSOL, right? Like it just goes on and on and on. All these different options, and they're really kind of purpose built. Okay. You could, and sometimes you would, put Gauss points, put your degrees of freedom on your Gauss points. And there are some cases why you would want to do that, but they're actually very infrequent. Generally, what you're going to be doing is you're going to have some kind of shape here, and you're going to evaluate the shape at those 2 points, at your Gauss points, rather than putting your DOFs. So this would be your DOF, your value at the nodes, and then you would use your shape to calculate what your Gauss points would actually be. And I think that the dominant reason for that is a continuity, because Gauss points are always going to be inside your domain, so you would have no continuity between different elements. Okay. Lagrange elements. You guys remember Lagrange interpolation functions? You remember me saying that they're just going to keep coming back and back and back? Here they are again. Okay. These elements are defined. Yeah. So because they're interpolation functions, what you have is a value over here, a value over here, and you're going to interpolate somehow between those two values, right? Is it going to be a line? Is it going to be a quad? Is it going to be a cubic, right? Depends how many points you have in there. What that means, though, is that you at least have values, your DOFs, at your nodes of your mesh. Okay, this is the default of COMSOL, by the way. If you remember, because all of you guys are obviously remembering everything that's all in the notes, right? Lagrange elements have this nice property. Sorry, Lagrange interpolation functions have this nice property that the one that's associated with a particular node here is only 1 at that node, and it is 0 at all other nodes, which means we're going to have one function that is, sorry, 1 here, 0 at all the other ones. We're going to have another one associated with this DOF that's 1 there, 0 at all the other ones, which makes finding our weighting coefficients super easy because all we've got is a single value associated with each shape function. If we had, so, oops, you just jumped to Colab. Still something funny going on with the book. So if you're following along, launch the Colab one and just run it. Okay. You guys see this okay? We can choose different types of Lagrange interpolations going from here to here. Okay. The first one is going to be a 0. It's Lagrange element order 0. And the way that you're doing order 0 over this element is a single point. Typically, you would put that in the middle. Right? And now you're just going to have a constant all the way across your element. That's the easiest one. Note that you no longer have the values here and here. Right? This is actually called a discontinuous Lagrange element. But it's the same, it's degenerate with the continuous one. The next one, so order 1 elements have your values at 0 and 1, here and here, and you're fitting a straight line, right? Order 2, which is again what COMSOL uses as default, has 1, 2, 3, and you're fitting some kind of quad, right? Third order, etc., etc., etc. Go back to Lagrange elements, or sorry, Lagrange interpolation, and you'll find this function again. Let's see what these guys look like. Can I make this bigger? Yeah. How's that? All right. So order 0. So this is our element between 0 and 1, right? Order 0 Lagrange elements only have one function, and that is a constant going all the way across. They don't have nodes at either side, so it's discontinuous. There is no continuity whatsoever between like one element and the other one. But there are still reasons why you would want to do this. For the interpolation functions 1, what you're going to get are lines, right? You're going to have one that's going from the top, from one node down to 0 on the other side. You've got another one from the other side that's going down. 2, you're into quads. So you've got nodes, you've got your values at the nodes, you've got the one in the middle, and now you've got this basis of polynomials, of quads, that are going to add up to another quad. A sum of quads is quads, right? But every single one of these is 1 only at its associated position and 0 everywhere else. That's the key there. You can go up to 3, right? Now you've got cubics, but it's still 1, 0, 0, 0, right? 1, 0, 0, 0, 1, 0, 0, 0. You're still maintaining that property, but now you can go algorithmically up and up and up. You can do it in 2D, 3D, ND. I've never seen an FEM code that goes past 3D, actually. Okay. Can I get out of full screen? Let's see. Yeah, okay. So we spoke a little bit about continuity again. Because the elements share nodes, typically any DOF that's defined at a node is shared on either side. Right? So here, if we're doing Lagrange elements order, I don't know, order 2, we're going to have a node here, we're going to have a node here, we're going to have one in the middle. It's going to look something like that, right? We're going to do it over here too. So we have one, another one here, another one here. We're going to have a quad or something like that on that side. But because this node is in common, we've got that continuity. We do not necessarily have gradient continuity, right? Unless that DOF said explicitly the gradient, and then you're shared. But in general, you're not going to get it, which is why like COMSOL tends to look faceted, right? Like when you look at the solution, it looked like it was different shapes. It's also how like video games are also colored, right? Like you kind of see that faceting all over the place. Oh yeah. This is not always the case, actually. 150 variations of finite element method. I'll show you guys something that will like make you pretty upset, to be honest. If you're doing Lagrange elements order 0, then you don't have these guys at the node, and all you've got are these constants on either side. There is no continuity here. You could extend that idea and say even with Lagrange elements order 2, you could break that continuity. It's called the discontinuous Lagrange elements. Very useful for advective equations, right? Because they advection that features the sharp gradients tends to kick up a lot of noise when you try and do anything with them. And these discontinuities actually damp out the noise. Unfortunately, you've also increased the number of DOFs in your system, right? Because now you've got 1 and 2 on the other side. Again, more advanced topics. Okay, illustrative example. Let's do 1D Lagrange. I'm going to jump over here again. No. Away. Gotcha. Okay. So 1D Lagrange elements are lines inside your element, right? And the continuity implies that you're sharing vertices, which means you would have something, your shape function is going to look like a tent, Sometimes these guys are tent functions. Got that. Got a few here. So Lagrange order 1 says that on this element, you've got a line, and this shape function is going to be 1 at that node and 0 over here. But it's also shared with this guy. So you're also going to be doing that, which looks like a 10. Let's try and actually reconstruct one of these guys. There's the code to do it. And this is a Bessel function, right? The approximation to this is being mapped out by the red dashed line here. And all we're doing is we're just summing all of these individual tents. I can barely see those colors, eh? Is that better? Worse? Right? So the value here has this value. You've got your tent. Over here, you've got this value. That's that tent. And when you sum them up together, you get sum of lines is a line, right? And then you go and you go and you go all the way over. Note that you don't need the same mesh size, right? So even just by putting two of these guys close together, you can still get a bit better resolution there, right? But there's no problem with being able to do that sort of thing. And I think this just randomly generates this. So you want to see other examples? Yeah, there you go. Like, look at this guy. Now you've got super good refinement over here, which is fantastic. And then you've got this massive stretch over here, right? And now you can see like why you would want this irregular meshing part. Because here it actually does kind of look like a line. Here there is good curvature. It's completely coincidental, right? But you can still build out and kind of scaffold this thing. Okay. Let's see. Through Lagrange interpolation. Oh, Isabel?
Sorry, I just had a question to clarify.
Yeah.
So the Lagrange we were looking at before with the different orders, is it? I may have confused myself, but for the Bessel function that you're showing there,
yeah.
with the kind of tent idea, is that using the order 0 order 1? Because I know we talked about it being the straight lines.
Yes. So that's using order 1s.
Order 1, because then it's not straight like horizontal, but it's straight between 2 points.
Correct. Okay. Correct. Yeah. So the question was how these tent functions are being built using the Lagrange interpolation functions. These are order 1, which means it's a straight line. But the difference between order 1 and order 0 is that it's a straight line that's at an angle. Order 0 would be flat. Just flat across everyone because it's a constant.
Thank you.
Okay. You're welcome. Okay. Extension to other dimensions is pretty easy, at least with the Lagrange interpolation. What you end up doing is you just kind of subdivide things wherever you're, if you were doing lines, if you were doing Lagrange elements order 1, you would just need 1, 2, 3. That would give you your flat surface over here, right? If you're going to subdivide that, you're going to increase the element order. I think you would have to go there, 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 and then the next one after that one would be this guy, where you have 2 on the side, 1 in the middle. If you want to do quads, they're there. 3-dimensional equivalent. And if you want to get real nasty, you go to the periodic table of finite elements. And I can't even read this. I'm not going to lie. This is like high math formulae that kind of go into if the degree of freedom is your curl, for example, which is great for, what's curl good for? Everybody should be like, at one point, all engineers should be doing this, thinking about like curl. In what course are you like holding yourself for comfort thinking curl? Electromagnetics, guys, come on. EM is all over like curl and everything, right? What was that? Eddy currency, right? Right? Super nasty. But you can imagine like electromagnetics is a slightly useful field in engineering and in like modern society just a little bit. So like all these mathematicians went in and were like, yo, if we do, the vector and then the tangential normal component of the surface sides here, then we can get a family of elements that, and then I just kind of black out. If anybody's really curious about this, by all means, here is the background. Knock yourself out. Don't come to me. I can't help you. This was this periodic table of finite elements was built out of a software package called, I think that was Phoenix, F-E-N-I-C-S. Finite element. It is a research grade. I would call it research grade finite element. It's also what I use in my group apart from COMSOL. There's like there's the Phoenix Firedrake side, then there's the COMSOL side. COMSOL is obviously like industrial, but Phoenix can give you flexibility that COMSOL can't. It is like run by the mathematicians with a bit of engineering in there. So for them, like being able to do the table of finite elements was like a big thing. And for us, it's a little bit much. Okay. Ooh, there's the other one. Previously, we mentioned if you're meshing your domain and you're cutting it up into different triangles, to show you. If you made those triangles infinitely small, you would get the exact solution. Right? Anybody think of the other way you could get the exact solution? There is another way. Even with a mesh like this, it would actually be possible to get the exact analytical solution, which is the second finite. Yes. So, good reading the notes. All good. So one way to do it is to make like the element infinitely small, and then every continuous function when you sample it over an infinitely small space becomes a point, right? So you could do 0th order Lagrange elements for an infinitely small mesh, and you would exactly recover your analytic solution. Or you make every single one of these have an infinitely high dimensional polynomial. And now, even though you've got these things on either side, you can still recover the exact solution. So the finite, the second finite, is the degree of your polynomial, or more accurately, the degree of your shape function that still has some kind of, okay, bringing it back to like the first class. If we had an infinite order polynomial, we could recover the exact solution. What is the name of the phenomenon? Right? That's consequent from not having an infinite polynomial. What kind of error is that? Truncation error. If you expanded your function through Taylor infinitely, you would get your analytic solution, but you have to truncate it somewhere. And as soon as you're truncating, it's truncation error. That's all this thing is, right? Okay. How much time do we have left? 15 minutes. Okay. Should we do some nasty math? Yeah. All right. Let's talk about the weak form. Right? Okay. How to go about this one efficiently. Okay, so we talked about the MWR, right? The minimized weighted residual thing. And we talked about how that was a solution to the problem that was kind of weaker than our normal solution. So let's say, because the opposite of weak is strong, this is the quote-unquote strong form. Let's say temperature by time is equal to negative divergence of flux. Everybody good with that one? Excellent. It's also here. What am I doing here? Yeah, okay. Why did I do it like that? Oh, yeah, okay, I remember why I did that. Okay. So if we're going to solve this in numeric methods, right? What we have to do generally is take this the time derivative, and we're going to do like forward, backward Euler or something like that, right? So let's just keep it simple. Let's just say our current solution minus the previous one divided by our time step. We rearrange that and we get something that looks like that. Yeah. Okay. So we've got, this is t minus, just call that t naught over delta t is equal to, bring that to the other side. Okay. What we're going to do now, this is another way to get to the minimum weighted residual. Any question? Okay. Yep. What we're going to do now is we're going to multiply everything through by this test function. We're just going to postulate that there's this test function that we're going to multiply everything through. We're going to call it v. You want me to keep to u, or can I just go ahead with a little coordinate change? Okay. All right. We're going to call it v. We've got vt, vt naught. Yeah. Delta t grad j. I left off a v, right? And then we're going to integrate the entire thing. Because again, we're looking for the minimum weighted residual over the entire domain. We're just going to integrate over the entire thing. That's this guy. And now this is the magic. This is super, super useful. This guy here, does this remind you of anything? Right? Integrals you can split up. So we're going to integrate over everything on the side here. That's a scalar. That just comes out. And we're left with this. Integral of some scalar times the divergence of a vector field. What do you say? Which one? Divergence theorem. Yeah. Did you say Stokes before? No. Yeah. 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 Right. So it's Stokes theorem. It's divergence theorem. Right. And the way that it works is that this like manipulating it like this way, I could never wrap my head around. I always have to go the other way. The only way that I remember that step is chain law. I always have to rearrange chain law. Right? So if you have d of uv, this guy, du dot v plus u dv. So I always think about it like this. Integral of the divergence there is equal to, this guy is the divergence of the vector flux times a scalar, and then you've got the integral negative of gradient of the scalar times the vector field. So you do that. Sorry, this is integration by parts, the first step, and then you apply divergence theorem. Then what you say is volume integral of divergence. So you've got a scalar times a vector field. Scalar times a vector field is still a vector field. Volume integral of divergence of a vector field is the surface integral of its normal components, right? Which is students moving around inside a classroom. Everybody has their own direction. That's your vector field. How many in the class at a time, right? I can either integrate over everybody's individual movement, or I could just watch how many people pass through the door, right? That's your divergence theorem, right? So what you get is this guy comes down to this one. Lambda here is just my expression of J. But we have done something very, very interesting here. First of all, we don't know beforehand what our test function is. It could be anything. But almost definitely, if we're doing Galerkin method, it's going to be something simple, which means it's going to be a polynomial. And the gradient of a polynomial, super easy to know. How many derivatives are there of our unknown field at this point? See if I have a better one down here. No. I should put in a better one for next time. Right? So J here, right? Originally, originally J was, why don't I have my flux equation here? Okay. Sorry, I need to go back and add to this one. J was originally negative lambda. I'll try and keep to this notation. So when you did this, negative divergence of J, what you would get is divergence lambda. Everybody follow that one? How many derivatives are on U? Right? So you've got the divergence of the gradient. First in time, second in space. How many gradients are on U now? This is the weak form at this point. Up here, right, if we write out what J is lambda grad U. Sorry, I'll update this for tomorrow. Here we have two derivatives on U, right? Because we've got divergence of lambda times the gradient in U, two derivatives. But through this magic, we've only got one derivative in U. And we've shifted one of those derivatives magically onto our shape function. Okay? We have replaced our second order derivative with the product of two first derivatives. Why is that important? Because if you've got an element that looks like that, and you've got one line on one side and one line on the other side like that, does a second derivative even exist for this one? Technically, no. Right? Because you've got one value here, you've got one value there, the limit does not exist. The limit of those two slopes does not exist. Second derivative doesn't actually exist for this. But when you put it through the weak form, it doesn't need to exist anymore. You can still get the weak solution, even though the strong solution cannot be satisfied. That's the magic of finite element. There's something else here too, though. Who's finished assignment 5? Okay. What did you do with lambda when lambda became temperature dependent? Yeah. Did you do chain law? It was inside the divergence. All right. Well, if you haven't, go back. Right? In finite difference, when you do that, what you're going to get is your divergence dot lambda grad t, which means your divergence, your lambda dependence is inside the divergence, and you're going to have to do chain law here in order to get the correct solution for assignment 5. With finite element method, you've actually taken your thermal conductivity out of the derivative. You don't actually need to do that anymore because it's not inside there, which is Super, super useful. Yeah, that's this part. Another part is this magic term here. So now what we've got is integrals over the domain and integrals over the surface. We've got integrals of your surface, your normal surface flux, otherwise known as your boundary condition, right? If we have our boundary condition given as one of the knowledge pieces of the problem, we can put it implicitly into our equation. The other way that we would have to do this, remember we talked about finite volume also has this property. Finite volume, you can also just put in your surface flux directly into your equation. You don't have to do any kind of manipulation. If you were doing finite difference, and I told you that J was equal to 10 over here, right? J is equal to lambda grad T, which means you kind of have to force these guys to have a certain slope in order to maintain that boundary condition. In finite element method with finite volume too, you don't have to worry about it. You can put it directly into the mathematics itself and let it find the best solution. More degrees of freedom, more flexibility in the, it's an optimizer, right? Because you're minimizing something, right? And it's going to find a more natural solution, which is good. Yeah, I talked about that one a little bit. All right. One more thing, and then I'll let you guys go. This is I mean, the weak form is a pillar of finite element method, but honestly, like weak form existed before FEM came along. FEM uses weak form. Another nice thing about the weak form is that you have, first of all, this is basically minimum weighted residual again, right? All we've done is we've used the test function and we've arrived at the same idea. We're integrating the test function, but now we've manipulated this and we've actually shifted one of the gradients onto the test function. Test function is known because it's some kind of polynomial, which means that it's even expressed in terms of fixed values, because the test function as a shape function is just one of these prototype things. Super easy, makes actual assembly of this stuff and actually building our systems, we'll see tomorrow, really easy. Nice thing about the weak form though is that we've tied in what's going on inside our domain to what's going on the boundaries. And we've done so in a mathematically robust way, which means if, for example, we want to do something like back to electromagnetics, where all of our physics happens on the boundary of our condition, of our domain, because of skin effect, we can actually isolate physics to the boundary that doesn't exist inside the bulk, which is kind of a weird way to do it. Another big one is surface absorption. If you're doing a chemical reaction, all your surfactants absorb onto the surface and then they diffuse and react. You have different physics that are operating on the surface. FEM can handle that completely naturally. Super, super useful. Anything to do with antenna design, for example, all uses FEM for exactly this reason. Okay, that's all I got. Okay. Last time we talked about boundary value problems being called the strong form versus the weak form. And this all had to do with whether or not we were including the, well, no. It amounts to whether or not we're including the second derivative of our function. MWR kind of leads to this weaker form, which has weaker requirements. We can mathematically, robustly say that we found a solution to the MWR when we can't do it with the strong form. Okay, so I'm just going to run this through again because weak form conversion is actually pretty easy when you get the hang of it. It looks a bit complicated until you've done it once or twice. COMSOL is doing it. The way that COMSOL works is that you have parameters that you put in certain fields and it's pre-calculated everything. So it's actually done all the weak form conversion for you. And if you know where to look, you'd be able to see what form it is, right? But otherwise, you just kind of like put in the coefficients and it does the rest. Okay, so let's say you have, right, temperature by time is equal to the divergence of a flux, which is divergence lambda grad T. Okay, what we're going to do is we're going to, how do you guys want me to do this? Do you want me to keep it like the time derivative, or should I expand it out into the finite difference? I can keep it as time derivative. Doesn't change anything. I'll do it like that. All right. So what you want to do is you want to take this equation and multiply through by a test function. It is just a function, right? And you've got a line, you multiply through, you can always multiply an equation by a function, right? No problem. So what we're going to do is we're going to say, there we go. We're going to call our test function v. We're going to worry about what it is later. And we're just going to multiply through is equal to I'm going to try and write this a bit closer so that I can write more than one thing on the board at a time. There you go. Anybody who's been to my office will have seen my whiteboard. That's why it's so big, because I like to just kind of write everything on top of everything else. Okay, so nu here, or v, or whatever you call it, is our test function, right? What we're going to do then is we're going to integrate onto both sides. Going to integrate the whole thing. I'm going to replace this as j for now, okay? Just for ease. Is that okay? And now we're going to take this and we're going to do integration by parts, right? So this guy becomes, let's see, how does this go? So this is where I always have to write this stuff out, right? duv is equal to du v du plus u dv. This guy is this one. So it's going to be equal to the integral of divergence vj minus j grad v. Okay, and the integral you can always split up. So you just do one of those guys. So far, so good? Can you guys actually see that, or is the podium in the way? Ooh, shouldn't do that with a coffee cup on top. Okay, and now you do the magic. This is the divergence theorem, right? You have the integral of a divergence of some vector quantity, which you can always rewrite as a surface integral. So this guy becomes, I don't remember, how do you guys write surface integrals now? With the circle in the middle? Okay, yeah. I've seen it written out as like that. I've seen it with that. Okay. Okay. All good. As long as you guys know what's going on here, I'm really bad with math because I always forget to write the, what do you call it, the differential over here. So technically this would be d omega, d partial omega. It's too much writing. I always just bury it in there. Engineering approximation. Right? And then you get this guy. And here, I'm going to write it out over here. Our final form is going to be integral time is equal to, here, I'll do it like this. Come on. Third time's the charm. This negative comes out with our expression for J. Right? This negative cancels. We're going to get lambda grad T grad V plus, not so sure about my signs here, and this is the normal flux. Does this make sense? So you've got some integral over your test function times your time derivative and temperature. What do you want to do with the time derivative? You do some kind of discretization. You do forward, backward. Backward is always convergent. Blah, 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 blah. You get this guy, which is your lambda, thermal conductivity. And now instead of having the T squared that you would have here, right? If lambda was constant, you would have something like this, right? Your Laplacian form there, you don't have it anymore in your weak form. Which means that if you have a solution that's made of these straight lines, I'm repeating myself from last class, right? In finite element, what we're going to do is we're going to be approximating the solution on the intervals with something that could be straight lines. Maybe they're straight lines, maybe they're parabolics, whatever. Let's just consider straight lines, right? This guy does not have a second derivative. Therefore, it can never solve this. It is not an admissible solution to this. But it can solve this guy. Because it doesn't require the second derivative. All it requires is the first derivative and a way to calculate integrals. And how do we calculate integrals when we actually have freedom to move things around? We use Gaussian quadrature. Okay? And that's going to come out on the final part here, which is assembly. Any questions about the weak form? If you ever get into something beyond COMSOL or ANSYS, if you go Moose, Bison, Phoenix, Fire Drake, advanced COMSOL usage, anything like that, you will probably be working in the weak form. This is the natural language of the finite element method. It's also a way that you can get into Lagrange multipliers, but again, we touched on that a little bit, but it goes a lot deeper than that. Question? Where, sorry, this one? This one to this one? I just expanded what J is so that I could show you guys that it's only dependent on the first derivatives of your temperature and your first derivatives of the test function. Probably. I'm terrible with negative signs. That's why I always throw it in Wolfram. Let's see. That guy cancels out with that negative. So no, yeah. I think I'm okay with that one. Okay. The other nice thing about this, again, going back to assignment 5, when you do this guy, your lambda is inside the divergence, right? So you're going to have to chain law that. And if you didn't chain law that, sorry, right? You're going to have to chain law it. In this case, lambda is outside of the gradient, which means that you don't need to use it just for writing out that equation. You will actually need to use it when you go to solve it because you're going to be solving it with the root finder. Root finder is typically Newton, and Newton requires the derivative for the root finding algorithm, Newton-Raphson. All right. Any other questions on weak form? It's actually super easy. I've got to say, like, once you do it a few times and you realize, like, so for example, if you had a heat source, I love throwing in heat sources here, right? All you would do is just follow it through exactly, right? And it just falls through without changing anything, really. If you had anything else that you wanted to throw in there, any other funny terms or anything like that, super easy to do. It's just like chain law, rearranging integration by parts, and then Green's theorem to get the surface integral. What was the other thing? Oh, yeah. With the strong form, you would have something like this, but this by itself would not be your complete problem. This by itself is not a well-posed problem because you need the boundary conditions, right? You need to say that T is equal to something on the boundaries, or slope of T, but typically J is equal to something on the boundaries, right? And then what you would do is you would have to solve your strong form and somehow insert your Dirichlet-Neumann conditions. Weak form is different because weak form explicitly has your surface fluxes. Okay, you can put that guy directly into your equation, and now you're not solving the strong form subject to your boundary conditions. You are solving a system which includes your boundary conditions directly. And if you wanted to get fancy and you wanted to be super general, you could actually throw in other physics over here. And this is where it gets super weird. So a good one for that one is chemical absorption and transport in material, right? Typically what you would have, zirconium. Zirconium in, in pressure tube material in your coolant, right? Some of the hydrogen gets into your zirconium and embrittles it. But it's not so simple because some of the oxygen is also on the outside of your zirconium, forms an oxide layer, which is super, super thin, but effectively prevents the hydrogen from getting in, which means that your surface physics is actually a little bit different from your bulk physics. The reaction rates are different. The chemical potentials involved are different. The chemistry is different, right? What you can do with finite element method is you can actually define different physics on your boundary than what's in the bulk. And it just gets wacky like that. Electromagnetics is another big one. I did one project that was it's actually really cool. Okay, I'll tell you guys about this one because it's actually really neat. For fast reactor fuels, you want smaller pins instead of the big thick elements. This is story time, right? You want the small pins, right? But you want them to be super, super hard and super resilient steel because you're going to go up to super high temperatures. I think the maximum fuel temperature in this was like 2,500 Kelvin or something like that. So like super high. You have all this fission, no problem. They use something called ODS steel, oxygen dispersal strengthened steel. And the way it would work is that you would kind of like inject oxygen into these things. But then there's a problem with how you seal your tubes. This is a bit of a roundabout story. Apologies in advance. Because if you heat treat it, normally you would like heat it up and like weld it together, right? But by welding it, you're going to destroy your oxide strengthening. So you're going to ruin it, and then it's going to be a weak thing, and then you're not going to have it. So this is what they did. They had a fuel pin, which was less than a centimeter across, right? And it was so you have a tube there. You put in a plug that you're going to seal it. And then you put this guy into a copper block that is roughly something like that. And you walk next door to your capacitor bank. And their capacitor bank was, I kid you not, about the size of this classroom. It was designed to charge up capacitors. And at the button, right? Sorry, they would put a little copper sleeve on top of the pin. At the press of a button, all that power would be shunted through this copper block. Okay? You get induced current in the little copper ring, like massive copper block, room size of capacitors, little ring. Okay? You get a counter current in the ring, and it pushes away from the block, so it collapses the tube fast enough and hard enough that within 1 millimeter worth of acceleration, by the time it impacts the plug, it achieves solid state welding. Shock physics. So what you do is we did like micrographs of this stuff afterwards, and we actually found that the solid, like normally it would be something like this. That would be like a little bit of welding, right? I don't know. This thing actually looked like frozen waves that had like smushed together. It was insane. It sounded like a shotgun, like every time they pushed this button. But why on earth I'm talking about this? Electromagnetic induction is all about the skin effect. So if we're looking at like how to actually put that together, and that was my job, that was my participation to actually model this thing, right? I didn't want to model a giant copper block when all the electrons were localized to honestly like a couple microns from the surface. So what you do, you need the three-dimensional topology, but your physics are actually happening on a 2D manifold embedded in 3D space. And you can do that in finite element. And it works super easy. And that was super cool. Unfortunately, it didn't work. The technology didn't seal enough. Yeah. Apparently, that's also how they manufacture car doors. I think any kind of like modern metal forming is all electromagnetic pulse technology because it's super fast. You bring in a sheet, you fire your capacitors, you bring it out, you charge up in the meantime, you bring in your next one and you do it again. What was the other one? Pharmaceuticals. I think this is actually how they compress the pills. So you make a powder. How do you get the pills? You don't want to heat treat it because then you're destroying all your chemistry. So you just slam it together with enough force, and it doesn't want to fall apart again. All right. And electromagnetic pulse technology is a great way to do it. I thought that was pretty cool. And honestly, like the acceleration required over like this much space, massive, massive. Okay. We talked about the boundary conditions. So Neumann conditions are integrated through the, I shouldn't say integrated. Neumann conditions are inserted into your math explicitly as a separate term in your equation, right? Dirichlet conditions, t is equal to something. All you do is you just pull a bait and switch. That's all you have to do. From your solution vector, which is your temperature profile everywhere, you just say, hey, these guys are on the boundary, pop them out, shove in your Dirichlet condition, and you're done with that one. Unless you want to do Lagrange multipliers, but again, that's a bit too advanced. Okay. Let's do discretization. You see why this is like the last chapter in here, and like there's not even an assignment on this. Like it's too much. I think when we do swap them and put this one in second year and then have the multiphysics course in third year, I think that makes a bit more sense because, but even then, like you guys all got through, presumably, you guys all got through computational multiphysics. I'll see you in a month who's back, right? Without having known any of this stuff. And this is like the blessing and the curse of modern technology, right? Like all this is hidden. You guys had no idea all of this stuff was going on in the back end, right? You click the button, something colorful appears. Right? Yeah. Hey, Dr. Mellon, why is this converging? I don't know. That's a TA. Try smaller mesh. Okay. Let's go through how you actually discretize this stuff. What you're left with is going to be something of this form, right? You've got integrals over your domain here. I wasn't so sloppy, but I still left off the differential here, right? So I'm still half sloppy. Okay, you've got an integral of normal terms like that. Did I write out where the thing was? No, okay. I'm just going to write it out to refresh memory. Oops. Okay. We are going to say that our solution, I'm going to switch notations here. Our solution, u of h, is equal to the sum of, I don't know if that's supposed to be an omega or a w over there. It doesn't really matter. We've got our weights times our basis functions. Okay, so literally all we're doing is we're saying that our total solution is equal to some weighted sum of our bases. Our bases are going to be defined depending on the elements, depending on the placing of the elements, the interconnectedness, blah, 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 blah. That's what we get. Okay. We're going to have terms of the form integral uv. So this one would be, shame I just erased it all. Anything depending on temperature. Do I have it up there? Okay, well, here's the gradient into the two of them, right? That guy is going to be this guy. This guy was, oh, the time discretization. That's right. Since we have, so just to backtrack a little bit. You know how we have this guy, right? And we do the integral of this. This guy, we're going to write out, I don't think I even need to say, okay, t minus 1. Okay, so this guy, we're going to do a finite difference form. And we're going to say nu t, let's just keep that as t, minus t minus 1 over delta t, backward Euler, right? Expand that guy out. We bring the t over to the other side. We multiply through everything. Delta t times blah, blah, blah. Vt minus integral of v t minus 1. This guy, when we expand it according to that, nu becomes our shape function. T also has our shape function. We're doing Galerkin. By, right? We get something like that guy, and that's going to be our first term. Second term looks like that, t minus 1, and then we've got our delta t multiplied through by our boundary conditions there. Since we have defined our shape functions, phi I, as only being non-zero on the element, right? Depending on the type of shape function, they're going to be 1 at particular nodes, 0 at all the other nodes, but even beyond that, they are only non-zero on their assigned element, which means it's something called small support is the technical term. I'm sure like mathematically there's a whole like field of study about small support, compact support functions, something like that. What it means for us is that when we go through this and we're going to start integrating between all the different permutations of shape functions, all the different indices, j and I between these guys, almost all of them are going to be 0, except within the particular element. What do you suppose that means when we look at our linear systems? What does it mean when most of the things are 0? Right? Which is the saving grace. Okay? You're going to see how that works. Typically, so it's for the shape function, the combinations of the shape functions, but also their derivatives for the exact same reason. If your function is 0, your derivative also has to be 0. Okay? Matrix assembly is actually one of the most costly steps of FEM solution. So if you watch the console log, eventually like it would keep saying assembling the system, right? And it's probably about like 40% of the time. There's assembly and then there's solution. Assembly itself takes like 40% of the time because it's building these things and then it's trying to solve them. Okay. We've got this guy. I changed notations again just to trip you guys up. Recalling that our solution is expanded like that. Our general test function v, because we're doing Galerkin, follows the same shape functions. When we put them in, we get something that looks like this. Okay? All we're doing is we're taking this term, we're substituting in these two summations, and we just get the sum over the I indices and the integral of these guys. But most of these indices are going to be 0, right? So how do we do the integral of our shape functions? In case you're thinking that I missed a step here. Discretization. How do we integrate? How do we integrate? How do we get these things? How do you integrate form? Okay. Riemann is one way. So that was the first way that we talked about. What else did we talk about in that section? You've got an integral here, right? What are we supposed to do with these? I just like kind of magically went from the integral here to a matrix, right? So I and j, those are the combinations. That's how you're getting the indices here. But how am I doing these integrations? I'm going to go patient dad mode here and just wait it out. That's fine. I don't mind. My daughter's all about high heels on top of crop tops. She's like 5. So yeah, I'm good at like waiting it out, I got to say. Okay, I'll give you guys some hints. Phi. So first of all, phi is actually the same function. It's some easy function. It's some like linear, quadratic, something like that, right? You want it like kind of a general form. It's fine. We could do some kind of analytic integration, but that's not the right answer in general. And the reason is because we're going to have triangles. It's some simple shape, but it's not on a simple geometry. So even an analytical derivative would be really hard to do. So what from our toolbox of numerical integration techniques are we going to throw at this guy? We know our function. You've already answered one. Okay, guys, no. Somebody else here. Come on. Simpson's rule. Not quite. So we've struck off Riemann, Simpsons. What else is there? You guys know. You guys already answered. Come on. Other people. I skipped class. That's not a valid integration technique. I'm going to start going across the room. I'm going to start at the back. What have we got? Gaussian quadrature. Why? What do you have to do with Gaussian quadrature? How does Gaussian quadrature, what do you do? If I'm integrating some function with Gaussian quadrature, what do I have to do in order to integrate it? Yep. Yeah, to like 1, 1, and then what? Yes. All I have to do for Gaussian quadrature is evaluate it at like 2 points. That's it. Right? So this guy, phi j, is equal to some coordinate scaling because you're in some weirdo triangle that has to be rescaled, blah, 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 equals phi I at some, well, it would be the product, wouldn't it? Right? So phi I times phi j evaluated at x is equal to what? In 1D, that was negative 1/3 square root, something like that, plus minus that. Okay? That's it. And I have done my integration. And what order is Gaussian quadrature? It does. That's why you got to come to class. Was that? It's very accurate. Does anybody remember what order it is accurate to? 4th order. When we derived Gaussian quadrature, we derived it assuming a cubic equation. And it will exactly integrate cubic equations. Anything past that is just like the corrective terms, which are order 4. Right? So if these guys are low enough order, right? If you're doing linear times a linear is quadratic, and this integrates it exactly, analytically exactly. If this guy is quadratic and quadratic, you're order 4, and it gets it honestly very, very well. And super, super fast. Okay? When you do that enough times, and you go through all your different combinations here, you're going to end up with a matrix, M. Okay? And your mass matrix is Yeah, your mass matrix so-called because it's associated with your first-time derivative. Since you're looking at this term, your mass is there. Think about a spring. You've got your mass times your acceleration. This would be your velocity term in that case. Okay, so it'd be more momentum than acceleration. Yeah. Does this look like anything to you guys? Where we're swapping notations again. Sum of I, Ui, Mij. That looks kind of weird, right? This is the index notation for vector matrix. Mij is a matrix, Ui is a vector. When you're summing over one side, what you're doing is a matrix product. Yep. It tends to jump around a lot between the index notation and the vector notation, just because otherwise, like, vector is very clean, but index is a bit more general. You can do a bit more with it. All right. Similarly, if you do that with this guy, right? So this is your divergence equation. You keep lambda out. You replace these guys with the gradients of this. Now you're going to do this again, Gaussian quadrature with the gradients, and you get your stiffness, right? And stiffness, again, you can kind of think of as a response to the force, right? Divergence of flux is roughly response to force. That's your stiffness. Yeah. This one came out terribly. Yeah. Since blah, blah, blah is known. Yeah, thank you. Okay. So, yeah, there's some super weird problem with this, by the way, with the book. For some reason, it is refusing to build the latest version and is magically reverting to the one from 4 months ago, which is why, like, even the logo thing hasn't been updated. We have no idea what's going on with that one. Hoping to fix that one soon. But all the content is by and large the same. All right. Finally, we can assemble our system. Okay. So we've got this big guy here, and we're just going to go through and we're going to replace everything. This is our index notation. We've got this guy. That's our mass. This is our stiffness matrix. This is our right-hand side. So the right-hand side, the vector is the one that's known. In backward Euler, that known quantity is your previous time step, right? You're going to solve for your current time step. That's going to be your so AX is equal to B. Yeah. AX is equal to B. Your X is your unknown, which is your current time step. Your B is going to be your previous time step, and A is going to be all that crap in between. We've got our boundary conditions, and we've gone down here. If you take out UH here, you can see directly the linear system now. Right? Take out that vector. We got delta T, lambda, K is equal to some vector, right? B minus Jn, right? Because you've baked in your Neumann conditions in there, that comes in there too. This guy turns into AX is equal to B, and we're back to a linear system again. Good? Okay. This is a nifty little equation, or this is a nifty little table about what they're all called. Okay. Yeah, we got time for this. We've got a matrix system. If your PDE is linear, we can just solve it directly, and it's sparse because of that nice property of small support. So let's do it like this. We've got 1D heat balance. We've got our lambda. We're going to change it to a nonlinear one. Going to show you what happens. From 0 to 10, we've got Neumann condition on one side, and we've got Dirichlet condition on the other side. Okay, and that's our inlet conditions there. we can calculate our mass matrix. Looks like that guy. And we're going to use our good old Lagrange interpolation functions, which are written like this. If you do it by hand, or even better, pop it into Mathematica, because who would do this sort of thing by hand anymore, right? What you're going to get is this guy on your prototypic element. So for this one, I just made a domain that was 10. Every one element was 1. So even that one from 0 to 1 had to be rescaled to -1 to 1, right? There's scaling and there's a lot of mess, but it's all algorithmic. You put it into the computer, you set it and forget it. Don't have to worry about it anymore. Stiffness matrix, you calculate out like that. You do your integration, you get this nice matrix equation. And these blocks belong to every single element. But now we have to stack it up and put it into the larger system so that we're able to solve all that simultaneously. It does imply overlap at common elements, at common vertices. So because we're doing the Lagrange shape function, right, that one had on our elements, it had values at the nodes. That's one. That's another one. This overlap means that whatever's happening on this element is added to whatever's happening on that element. So feel free to go through this if you really want. Oh, should launch this guy. Hold on. I was testing this code last night. It runs. Even gives the correct answer. Assemble a linear system. Yeah. Okay. Funny thing is, like, all the math formatting works just fine in Colab. It's only in the Jupyter book. Okay. And we've got our heat balance. And this heat equation is, if I'm not mistaken, this is the temperature over time. And just nice normal behavior, as you would expect. There is a little bit of an optimization when you go through all this stuff. It's not super easy to see, but M, where was M here? So my M matrix here is like an integral of shape functions over everything, right? Does that change with time step? No. So your mass matrix, as is, you don't have to reassemble every time. You can do it once at the beginning of your time loop and then just apply it over and over and over again. Your stiffness matrix, stiffness apply, is that time invariant? Stiffness matrix is this guy. Also integral over these shape functions. Stiffness matrix also not. You're also okay with that guy, but here you have two things. You have your delta T, which typically does change from one time step to another because you want the adaptive time stepping. Lambda. Thermoconductivity, even though you don't need to worry about the chain law, it can still change from one time step to another. So you would still have to rebuild this entire product for a nonlinear case. If you're doing a nice linear system, your thermoconductivity isn't changing, your time step isn't changing, you don't have to reassemble this matrix every single time. But in general, you will, because you're going to be like updating your delta T, your lambda, and stuff like that. Okay. Nonlinear case. What do you think we have to do? Got 8 minutes left. Just kind of scroll up there. It would change lambda. Yeah. So we're going to change from lambda is equal to 1 to lambda is equal to 1 plus u over 10. This should sound really familiar to most of you guys. What do we have to do? Anybody? I see a half hand. Yes. Yeah. Which one? Sorry. This one? It's your solution vector. Oh, yes. Yeah, that's your solution. So this would be lambda depending on t. Yeah, which you guys just did for your assignment. So, so what is that loop called? What do you do for nonlinear equations, guys? How do you solve a nonlinear equation? What's that? Not even. I just gave you a nonlinear equation and I asked you to find the solution. What do you do? Newton-Raphson. It's root finder, right? Just throw a root finder at it, which means even for the linear case, just throw a root finder at it and it's going to converge in one iteration because it's exactly the special case. No problem. Sparsity massively helps. Let's see what it looks like. So this is an example. I left that in actually because this gives you the wrong example. This one, I asked Gemini to take the previous solution and change lambda, which it did, but it wasn't smart enough, at least a year ago when I generated this, it wasn't smart enough to realize that lambda changing means that you have to use a root finder. So beware the pitfalls of AI with that one. So this is a solution that I got stepping through time, which is not correct. It shouldn't be of this form. So I had to reprompt it and say actually use a root finder, which it did, and then I got the correct solution. Is that actually changing? Yeah, just takes a while. Okay. That's all I got. So moving forward into your careers, because Gemini and all this funny business ain't going away, right? Try and remember that the big picture clues of like what you expect your method to do. Because it will happily go through this, right? And just say, oh, well, I'm just redoing that with a changing thermoconductivity. Because it wasn't smart enough, at least at that point, and having used like even Gemini 3.0 now, it's still not quite there, right? Like it will give you an answer, and it's going to be on you guys to figure out whether or not it's the right answer. So if you hit go and it solves like that, and you're doing a 3D multiphysics something like, no, that's not the right answer, right? If it goes through and it's not even like burning through a lot of memory for a nonlinear equation, something's wrong. It should be using some kind of root finder. It'll give you an answer and it'll think that it's correct, but it's I don't know. I don't know if the current models of the reasoning stuff will actually change that to the point where it'll be smart enough to understand that. But either way, like if you give it enough noise in your prompts, I think it's still going to find the wrong answer. In which case, it's up to monkey brain. Any questions? What happened to my sparsity plot? I had a sparsity plot. Didn't I? Thought I had a sparsity plot. No. Yeah. This one is so in the linear case for the FEM method, because your function is only depending on its own element and you're in 1D, it does form this nice banded structure. Kind of looks tridiagonal. Nope. I think that's 2, isn't it? Anyway, hey, it does form this banded structure. Anything past that simple one, anything that is more complicated than 1D is going to not have a banded structure. And that's going to be because of the different combination of your elements and their proximity to each other. You will still be sparse. You lose out on the banded part. Banded really comes out from finite difference. Finite element, you're going to get these beautiful symmetric patterns because what happens on one side generally happens on the other side too, but it's not going to be this banded, but it doesn't really matter because you can still use the sparse matrix solvers. Okay. Monday we'll talk about eigenvectors. Not Monday, Tuesday. Right. Have a good weekend, guys.